So we are now ready for testing and running our LSTM, and in particular, comparing it to the RNN. So the idea is the same that so it's the same idea that we had in the classical RNN. So we have YT, which is our data here, and we want to train it for the prediction YT plus DT in the future. So we use YT as our XT and YT plus DT as our training data, so that for every time point, we can make predictions for time point in the future DT. So the overlap of this is then our actual training data. And the extent on the right-hand side would be our validation data, because that's the data we have already. And then we look at the prediction we got from the vector XT, and then compare it to the shift by DT. And what comes after that is the actual prediction. And we did this already with our package, where we created this package for our classical RNN in the last lecture. And we will use the exact same structure for our LSTM. There's only one difference. What we want to do now is to draw a randomly chosen subsample from our time series, run a few iterations over this subsample, and then continue with the next epoch and draw another randomly chosen subsample, and so on. It's a bit like the idea of having a mini batch from the image analysis, because the entire data set was too large in this case. So we just randomly draw a subsample of images and train the neural network with the subsample and then draw another one. And the result, hopefully, will be something like that. So if we have a more complicated data set where we also have a long-term trend, that the LSTM is able to cope with that. So we will use a package that I have just modified based on the package we wrote for the RNN, and we discussed it thoroughly in the last lecture. So I will not explain those details again, but it's just the same structure that we're going to use. There are a few differences, though. For example, it's not only the LSTM itself that contains the learnables, therefore the memory. It's also the dense layer, dense 1 and dense 2, because remember, the LSTM created as an output just the state vector, but we needed these two dense layers in order to create the actual prediction y hat by transferring the state vector h into y hat. So it converted h into y hat. And we will also want to do this with a relatively small number of neurons. And then hopefully we will get a result which is a lot better. And that's what this plot indicates already. And that's what we want to see. We, of course, have a more complex, more sophisticated network, and it should perform a lot better compared to the classical RNN. And that's the idea of this section, that we run our LSTM and especially comparative performance to the classical RNN. So what I did already is that I created a new folder. It's just called package, where I just copied the RNN package from the last lecture, and has the same structure as before, and I rewrote it in order to adapt it for the LSTM. So it has the same structure as the RNN package, where we have one function that calls the LSTM for training, and it just initializes the LSTM, the dense layer, and all the optimizer. That's what we just did in the last chapter in this lecture here. Then it applies phase shift, and then it selects a subsample of the time series randomly and passes on through the forward method and run a few iterations over that, and also through the backward method, of course, and then picks a new subsample for the next epoch. And then at the end, it will create a few plots that you also see the progress, and it returns the LSTM and also the weights and the learnables from the dense layer. And we're going to need this for applying the LSTM to a new data set. And it does it by just running through the forward part, which is the LSTM cell. So it's completely equivalent to what we did in the lecture about the RNN. You see it's the exact same structure, only that's an RNN here, and we have an LSTM. So that's really comparable. So it's the classical RNN, and this is our LSTM. So again, if you're interested in details, just go to the lecture RNN from scratch. But it's not crucial for understanding this part. So just imagine everything that we discussed in this lecture in the previous sections now is put into a package. And now we want to test this on a particular data set, and we want to start with a relatively simply structured data set. So just just like our sinusoidal data set, where we have some noise and very predictable sinusoidal behavior. We don't have a long-term trend yet. We also want to test this, but let's start with a relatively simple data set, which has a certain length. So let me also just check the length, which is 700 data points. And now we want to make a prediction of 200 data points in the future, and we run a very simple LSTM, and then we want to compare it to the RNN. So let's, for example, run the LSTM here. And also I want you to understand what it does, of course. So we start with just 100 neurons, and then what is highlighted in green here, this is the subset of the data, which has just been drawn randomly, and every time it's a different subset. Of course, for this particular training data, it doesn't really matter where you draw it from because it's still the same periodic behavior. But you should see it always has a different size and always comes from a different location. And then it fits the data. And you actually see that after a few dozen epochs, it has a relatively good result already. So we're at 130 epochs now. So the loss is like 2%. So that's a pretty good result already. Of course, it's not perfect, so we can still modify a bit the learning parameter and optimize that a bit. So it's done now, and now we can apply it. So it's like 2%. Now we can apply it to the new data. Let's just use YT, because then Y hat is just a prediction 200 time points in the future. So if you want to plot this for X, we just need the same X vector. So we just have Y hat, but then we have to shift it by DT so that the plot makes sense. So let us just plot that. And here's the prediction. You see it's a pretty good prediction. And we can also continue this by using Y hat and putting this back into apply my LSTM so that you can stepwise predict the time series in the future. So this would actually pretty well. And let's try now the same thing, the same data set, the same shift in time, the same number of neurons, and also the same number of epochs with the RNN. So remember, for the LSTM, after like 60 or 100 epochs, we had a relatively good result. And let me also just delete this here. And leave the final result, like this one, that we really can compare. All right. And also what you see here on the right-hand side, highlighted in gray, this is the actual prediction. So let's do the same thing for the RNN, that we have a complete comparison. Let's even start with the same learning rate. Let's see what we get. Remember, the training of an RNN of the classical RNN was always a bit challenging because of the vanishing or exploding gradient. Let's see what it does. It kind of does not look so bad. but it's not as good as the LSTM. And remember the plot I showed on the in the slides. So after 800 or 1000 epochs, it actually had an acceptable result. So what you should definitely see is that the LSTM is way more efficient. So let me just rerun it again. So I think the difference now is clear. So it's the exact same training parameter. It's the same data. Here we have the problem with the gradient. So it failed at all. So I think you got the point that the LSTM performs a lot better. So let us now add the exponential trend, the long-term trend, just a bit. Should just be careful at the beginning because we don't want to stress it too much, but we of course still want to challenge it a bit. So let's do that and let's create a plot and let's see what it looks like. So we have a long-term trend. It's not really 100% linear, so it's a bit exponential. But let's run the LSTM and let's see how it copes with this long-term trend. We keep the same training parameter because it worked already. It's only 100 neurons. And let's see what the result is. It goes a bit up and down, of course. Again, I want to stress that we don't have optimized the learning parameters, although I have played already a bit with the momentum. And let's see how well it does with the long-term trend. So the loss kind of fluctuates, which is, of course, not ideal, but eventually it should find a nice minimum where it also understands the trend. So it's kind of approaching. So let me just pause it and then we can take a look at the result. So I played a bit with the parameter and I even made it more steep. And after 200 epochs, it's of course not perfect, but I think you can see that it goes in the right direction. So of course we probably would need a few more epochs, change a bit with the training parameter. I also now played or just tested 100, 200, 300 neurons and particular time shifts. But I think you see, even though it's not perfect here, it goes in the right direction. And by changing the learning parameter a bit, you will see that it will give you a nice fit. So the loss is like 0.4. If we just compare it to the dynamic range we have, which is something like 5 or 6. So let's divide it by 5. Then you have a rough idea about the error that we have here. So again, it's not perfect, but it goes in the right direction after 200 epochs. And now let's do the same thing with the RNN. So we have 200. We don't want to do that. So we have 200 the time shift is 200 time points. We also want to do this with 300 neurons and also 200 epochs. And also we want to have the same learning rate and that we really can compare it. So let me just delete everything from the earlier epochs. And you can also see, by the way, how it approached or how it's improving the fit. And now let's do the same with the RNN. And here we see already the problem again with the vanishing or exploding gradient. Let's keep it simple now. Let's start with 100 again. But you see, we always have this problem. And of course, if you use packages from Python, for example, then they kind of take this into account. So it will be a lot easier to deal with. So it's actually not so bad if you look at that. So it kind of understands the trend. It's 2 times less accurate. So let me just run this again with 200 neurons. So it's comparison that's a lot more fair. Well, but you see then, I guess that's the when we are overfitting. So it kind of does it, but if you compare it, so let me just delete this also here that you can just see the difference. So that was the LSTM, and let's delete this everything, and you see the result is not so bad. So we don't need this part here, so that we really have the comparison. So that's the LSTM, that's the RNN. Same data, same number of epochs. The only difference here is that we have fewer neurons. So we probably can still gain a lot when we change the learning parameters. So, however, if you really want to play with that, and I want to show you a few results. So if you really optimize a bit for the training, then you can have relatively good results after a few epochs already, and then 200 epochs. Then you have this kind of result. And if you run this with an RNN, you usually have this kind of result, which is of course not perfect. We got actually relatively good result as we were just trying it, but just that you have an idea about the overall trend. So in principle, the LSTM should perform a lot better, and it actually does it often when you just have a more complicated data set. And therefore, I want to compare this a bit. So in the RNN lecture, we created a classical RNN after 800, 900 epochs. We had no problems with predicting this sinusoidal behavior. With an LSTM, that was incredibly fast. That's what we showed earlier. And after dozens of epochs, then we have already a relatively good result. The RNN struggles a lot with the long-term trend. And also you saw we have the problem with the vanishing exploding gradient. Again, for actual software packages, those programmers took care of that. So that's not as flimsy as in our case. You can really jinx it actually if you like. If you add a few more features to the data and then compare the RNN with the LSTM. So for example, if you just add another change and multiply it with an exponential and so, I would really recommend to do that so that you just play a bit with data. So again, this was a lecture where we wanted to create an LSTM like the classical RNN on very simple with very simple programming. So there are no abstractions. There are lots of stuff to improve, of course. Also to improve the training. So you saw it's all not perfect and it's all not optimized concerning runtime. But the idea, of course, was to keep it as simple as possible that you understand how it works. And that's it. And I hope you could learn something. And I hope you enjoyed the course.